Hello, everyone. My name is Bilal Shahid. I'm a product manager at Juniper Networks, and I'm really excited to be here to share with you guys some of the work we've been doing to define the next generation of transport. We'll start with making a case of why choose segment routing as the new transport. We'll then get into details of SR use cases and different flavors. Lastly, I will give you guys a glimpse of some of the next generation segment routing architectures we are working on with focus on network slicing. So let's get started. If we look at networking industry overall, we see three key market inflection points. First, we see an exponential growth in number of IoT devices. According to IDC, there will be more than 41 billion IoT devices by 2025. Second major trend is 5G, which is not a hype anymore, and it's already here. 5G is a major step up from 4G because of its ability to connect billions of devices at a very high bandwidth. And finally, network traffic, which will continue to grow year over year. And the main driver behind this growth will be video, which will carry 75% of the overall traffic. Now, naturally, these trends are going to create some network challenges. We will see shifting traffic patterns. We will see highly distributed networking architectures with more traffic on the edges of the network. And we'll see metro becoming the new edge. Another requirement would be low latency networks. We'll see stringent SLAs for industries that have never been connected before, such as medical and auto industry. Low latency will become a de facto requirement. And all of these challenges needs to be addressed while keeping CapEx and OpEx optimized. Now, if we take a step back and analyze all these trends and challenges and identify what's the simplest way of addressing these challenges, we come to a conclusion that we need to modernize the network transport because network transport is something that touches every part of the network. It is the backbone of the network. So the question is, what will be the key characteristics of this modern day network transport? First, it needs to be agile and resilient. And what I mean by that is a technology that can not only support present day applications, but it is agile enough to adapt to the constantly evolving nature of the new network. It also needs to be simple and scalable to meet the exponential growth in 5G and video traffic. Lastly, it should support automation because automation enables easier management and centralized control. Now, this begs the question that which technology do we choose to design this next generation of fabric with? And this brings us to segment routing. Because at a high level, segment routing has all these characteristics we just discussed. In SR, state is not stored in transit nodes. A number of paths in the network can grow without increasing the state in the network, which makes it super scalable. And this is a very powerful thing as it takes a lot of state out of the network. It leverages TLFA, which is the most powerful fast reroute mechanism and gives 100% of coverage, and that within milliseconds. SR is simple, as no extra signaling mechanism is needed, which means one less protocol. And most importantly, it is based on the idea of true end-to-end connectivity with centralized control, which makes it very automation friendly. So you see all these characteristics makes segment routing much more flexible transport than any other transport out there. But how do we adopt SR, right? How do we make it work? I think success of any networking technology depends upon how well you provide the smooth migration or how well it works with existing technology. And this is true for segment routing as well, which is why migration is the key part of our overall strategy. And this brings me to the second part of my presentation, where we look at different segment routing use cases and what is our vision of SR getting adopted by different industries. What you see here is 5 different deployment options or use cases for segment routing across various industries and how they are being migrated to SR. The first use case is shortest path routing. This is your typical metro or enterprise use case where you're interested in shortest path routing along with the C&SP and you're using, let's say, LDP. This actually becomes perfect choice for migrating to SR. SR will give you all your benefits of SPF without any additional protocol or signaling. Now, depending upon your need, you can either decide to keep your LTP network intact or you can completely move to SR. We support both these use cases. Another use case we see a lot where we see customers who are still interested in SPF, but they need protection. For that, they're using RSVP just for FRR. Segment routing simplifies this TLFA, which gives you 100% coverage, and you are only using one protocol. TLFA is one of the most simplest mechanism to provide fast reroute for any topology. Furthermore, segment routing supports ECMP and any class states, which further enhances our goal of resiliency. And this brings us to our third deployment case, where if you want to use some kind of traffic engineering, but you're not interested in bandwidth. So I would say it's kind of like light traffic engineering. And you can do so by using on-box CSPF or dynamic CSPF. This will take IGP TE metrics into account and spit out traffic engineering path without even using a controller. So it's more of a traffic steering use case. And this is particularly useful when you want to use distributed model instead of centralized model for TE. Now, how about, let's say you want a full traffic engineering use case and you're interested in bandwidth or inter-domain TE or what we call end-to-end SR. And this will take us to our most advanced use case where you would definitely need a controller. And it's now very important to mention that since SR is stateless, in order to support traffic engineering, this state has to go somewhere. And this is where controller comes handy. Now, this can be either a set of controllers or one controller, on box or off box, but it is needed to carry the state and monitor multiple domains. And this pretty much covers all the use cases among different industry segments. And to summarize, I would like to say that we support all of these deployment use cases and all of these migration use cases. So now that we have covered different segment routing use cases and deployment options, let's understand what segment routing flavor best suits your network. There are actually 4 different flavors. First and the most popular option is SR-MPLS v4. It's based on MPLS forwarding plane with IPv4 underlay, which is the most widespread deployment. Standardization is very mature, operational understanding is very high, and this also does not need any new hardware change. So if you have a typical MPLS-based network, it makes it easier to transition to SR. I would say it gets my popular vote. The second option is pretty interesting, and for some reason, not very known to the world, but it is the most simpler option. And if you want to take your existing MPLS network to an IPv6 network, this is your option. This is exactly like SR MPLS v4, and the only difference is IPv6 underlay. Almost every hardware supports it. Standardization is very mature. No new operational learning is required. And to put it simply, it just works. The next 2 options are non-MPLS options, or we can say, IP fabric options, and they only apply to IPv6 networks. SRv6 uses IPv6 addresses instead of MPLS labels as SIDs. It brings programmability to the table with the instructions encoded in an IPv6 address. But using IPv6 address as SIDs makes SRH pretty inefficient if traffic engineering is required in the network. This is still an evolving architecture, and a lot of efforts are being done to improve, but still the support for brownfield networks are still not very well supported. This brings us to our last flavor, which is SRM6. This is Juniper innovation. The architecture is designed on the philosophy of taking all the good things of SRv6 and making it more efficient. This is also a non-MPLS IP fabric option. The key difference is instead of SRH, it uses CRH, which is a compact version of SRH, and it removes the inefficiencies. This does not overload IPv6 address semantics and uses existing IPv6 extension headers to pass the instructions. Like SRv6, it is also an evolving architecture, and its standardization is not very mature. Now, how do we choose between these different flavors? So customers who are already running an MPLS network and like it, the choice is pretty simple. If you want to upgrade your IPv4 network to SR and you're already using SR MPLS, SR MPLS v4 is your choice and is the most popular option and widely supported option. If you want to move to an IPv6 network and you're already running an MPLS network, you're in luck again, as MPLS just works with an IPv6 underlay. So MPLS v6 is the obvious choice. Both of these technologies are well suited towards brownfield deployments. For the customers who are either not using MPLS networks or want to move away from MPLS for some reasons, there are 2 choices, SRv6 and SRM6. They both are IP fabrics for IPv6 networks. We support SRv6, but if you're interested in traffic engineering, SRM6 offers similar functionalities with much more efficiency. Lastly, both of these technologies are more suited towards greenfield deployment. Okay, so now that we understand segment routing and its different use cases and different flavors, it's time to move to the final part of the presentation and talk about some of the next generation architectures and innovation we are doing with segment routing, right? I will talk about how we are addressing network slicing and what role a controller can play in an SR architecture. Every deployment scenario has its own set of challenges, and there will not be a single solution that will fit all scenarios. Therefore, we have developed few solutions that will work together and address all these sort of deployments. But first, let's understand network slicing. What is network slicing? Network slicing is a notion of dividing a physical network infrastructure into different logical networks, where each network slice or that logical network is an isolated end-to-end network designed to fulfill requirements requested by a particular customer or an application. No talk of network slicing can start without talking about flex algo. The idea is very simple, and it enables you to divide your network into different slices, where each slice is represented by a flex algo. Each flex algo can have different intent and purposes based on the need of the network or a customer. And each router can be part of one or more slices by contributing to that flex algo. So think of it as a concept of soft slicing where every slice is independent, not only for functionality, but even for the protection. Every slice is protected by its own TLFA. And this is very, very powerful concept. We call this intent-based slicing since every slice is mapped to an intent. For example, one slice can be best effort and other can be latency sensitive slice. This is also perfect for scenarios where we want to map multiple customers to one or more intents. One more advantage of Flex Algo is that it achieves light TE, goal with shortest path routing with single label, which makes it very efficient in terms of label space. This is the most suitable option for architectures where number of intents or slices required are less than 8. So this begs the question that what if we want hundreds of slices, or our definition of slice is not exactly intent. Rather, we want to provide a slice as a service where every customer wants his own slice. And this brings us to our next architecture, which looks at network slicing at a scale and addresses inter-domain network slices challenges. It's called express segment architecture. As we said earlier, that a slice can either be an intent or slice can take many other forms. But at its foundation, it's a customized representation of a network topology, along with an identifier that caters to the slice. Therefore, a slice in express segment architecture is composed of 3 main elements. First, a customized topology, a slice identifier for the topology, and one or more optimization functions that are applied to that particular slice or customized topology. Furthermore, as networks are getting bigger and bigger, their topologies are getting much more complex, which makes it harder for the routers and PCEs to process and distribute these topologies, especially when we are talking about multi-domain networks. We need a way to compress these complex topologies to reduce the size of traffic engineering database, and in turn, making it easier for the PCEs and routers and controllers to process and distribute. Express segments exactly does that. It creates a topology or a customized topology that inherits all the property of the original network, but with a significant reduction in traffic engineering database. This enables it to handle large multi-domain networks. It works with and without controller, which makes it very flexible. The architecture is brownfield ready and support all flavors of segment routing from SRMPLS to SRM6 and SRV6. Now let's switch some gears and talk about some of the distributed architecture we are working on, and it's called Seamless SR. This one is really interesting because it's a natural extension to Seamless MPLS architecture, which is widely deployed. So think of it as network of networks, where multiple completely independent networks are glued together through BGP glassful transport. In this architecture, each domain is completely independent and deploy any technology like RSVP, SR, FlexAlgo, LDP, or even IP fabrics. Each domain can also transition from one technology to another technology independently, which makes it ideal for brownfield networks. This makes it a scaled out inter-domain architecture, which provides end-to-end SLA paths with an extension to BGP and is suitable for 5G transport with an exponential node scale. Okay, let's talk about the idea. The idea is simple. A family named BGP-CT is defined. This family carries different color advertisements to the same loopback address. These multiple colors corresponds to different SLAs. Seamless SR solution also provides end-to-end low latency paths by using accumulated latency metric, which is similar to AIGP metric. Lastly, it provides an efficient means to achieve end-to-end network slicing as well. This strict slicing is achieved by maintaining transit states across the entire network, and per link slicing, which is very high number of slices, is achieved by carrying slice information in the packet without maintaining any transit state on the routers. In short, it becomes a perfect upgrade of your seamless MPLS networks. Now, whether we use express segment architecture or seamless SR, all of them are brownfield ready and works well with existing technologies. They also align to our vision of end-to-end SR. We see segment routing along with EVPN to become the foundation of next generation 5G networks. We also see network slicing become the de facto requirement of any new network design. All of our solutions provides a seamless path towards next generation of transport. We have working demos available of all these architectures, which are available on request. Okay, so far we established that one of the key components of any segment routing architecture is the ability to provide centralized control. And this brings us to our last piece of segment routing puzzle, which is a controller. We have developed a true vendor agnostic segment routing controller, which is called NorthStar. NorthStar supports wide range of network transports, open APIs, along with providing a great user experience and smooth migration to segment routing. NorthStar goal is to provide fully automated and programmable experience. NorthStar works in 3 basic steps: analyze, optimize, and automate. NorthStar learns the network topology using BGP-LS. It also gathers fine-grained telemetry information from the network. It then analyzes and optimizes all the information to take intelligent actions like raising an alarm in case of any anomaly or taking preemptive action to prevent congestion in the network. It then uses BGP SRTE or PSAP to pass that information to the network. So in turn, kind of creating the full closed loop automation. It comes really handy when you have to monitor the network with multiple domains. Then controller becomes the central entity controlling all the domains. Since our aim was to make NorthStar vendor agnostic, we added support to many open APIs and integrated it with many third-party tools, as well as internally developed Juniper applications such as HealthBot for applying machine learning and artificial intelligence to all the data it's gathering. NorthStar aligns with the Juniper vision of self-driving network and is deployed at many tier 1 network operators, and it completes our SR story. In the end, I would like to summarize by saying that we have developed a feature-rich segment routing solution, which we support across different families of our product. We have many deployments and production pilots in the works. We're continuously innovating and leading the pack with next generation segment architectures. Last but not the least, we have industry first true segment routing controller, also known as NorthStar. This brings us to the end of our presentation. I hope you have enjoyed the session so far and learned something about segment routing. The idea was to give you guys a higher level view of what are we innovating with segment routing. Thank you so much. Adios.